So we've been talking about Newton's second law, okay, for quite a while now. And obviously Newton's second law tells us that the net force that's acting on an object, that's probably not the best color to use, that the net force acting on an object is equal to m times a. Okay. What Newton's third law tells us is that if a force is exerted on one thing, that thing is going to exert an equal but opposite force back. Okay. Now, that means in an interaction between two objects, the force will be the same, but the accelerations could be different. Why would the accelerations be different on two objects if the forces were the same? Mass, exactly. Okay, this goes back to when we were talking about how a semi-truck and a smart car, when they collide, the smart car never wins. Okay, and that's because the forces exerted are the same, but the masses they're exerted on are different. Okay, so the force exerted on the truck by the smart car is the same as that of the truck exerted, on the smart car exerted by the truck. They're the same. The difference is mass. Okay, and so as a result, the accelerations are different, right? It's why I'm not going to win a sumo wrestling match, ever, unless I put on another 300 pounds. Then I might have a chance, okay? It's just a matter of mass. I could just take a dead run at a sumo wrestler, okay, lower my shoulder and hit him, and I'd just bounce off, okay? It's just a matter of their mass is so much bigger than mine that I'm not going to cause an acceleration, okay? It's not that they don't feel the force exerted on them by me. They do. They just laugh at me after because it doesn't cause any acceleration, or a very small one. Okay. Meanwhile, I'm laying in a pile with a dislocated shoulder, okay, looking pretty foolish. All right. So the thing we have to remember about Newton's third law is that all forces act in pairs. No force acts alone. Okay. Right now, gravity is pulling me into the floor, and the floor is doing what? Pushing back. That normal force is that paired force. Okay, it's the one that makes sure Newton's third law is obeyed at all times. If I push on something, it pushes back. Okay, it's quite simple. I mean, if I push on this desk, do I feel the desk against my fingers? Yeah, that's not because I'm pushing on the desk. It's because the desk is pushing back. Okay, that's what I feel. I always feel the reactive or normal force. I don't feel the force I exert. The object I exert it on feels it. Okay, so that's what normal force is. Okay, it's that reactive force that makes sure that there's always a paired force. Okay, and that's true for everything. Even in zero gravity, there's still going to be a reactive force. In fact, it's what all rockets and things like that depend on. When we watch those videos of the astronauts moving around in space, okay, the little jets that they use are called reaction control systems. RCS. Okay, the reason they're called that is because the pressure of the gases inside when it's released, okay, the container, the compressed gas container they're in pushes on the gas. That's what makes it go out. But the gas also pushes on the container, and that's what makes them move in the opposite direction. Okay, it's an action-reaction pair that we use in order to maneuver. All right, so Newton's third law is probably the most often misquoted or misapplied law there is in physics. Okay, Newton's third law is that every action has an equal and opposite reaction. Okay, that is Newton's third law, right? But for some reason, people try and apply that to like social situations, sociological, psychological situations, and it doesn't apply there. Okay, if I say something awful to somebody and they smack me in the face, that wasn't an equal and opposite reaction. It was probably appropriate because I said something awful. Okay, but people try and, oh well, that was weird. I guess every action is equal and opposite reaction. No, okay, it doesn't apply in those situations. It applies only in situations involving force. Okay. Okay, so if we're looking at, let's say, like a football game, okay, where we have, two lines and they're going to crash into each other, okay, when the ball is moved, okay, we're going to have action-reaction pairs there, okay. I'm going to feel the force of the other line on me, okay. If they move first, they hit me first. I feel that force, but they also feel the force back, okay. Sometimes you see this in like hockey and football and contact sports, where the person who initiates the hit actually gets hurt worse. Okay, and it happens fairly often. Okay, and it's just a matter of where did the force they exert get exerted back on them. Okay, that's why you want to be careful with like shoulder checks and things if you're coming in at an angle. Okay, if that force, if you hit the person square, your force acts on all of their mass. The force they exert back on you maybe only gets your collarbone and shoulder, but that's a lot less mass. Okay, and so it could cause more damage to that localized area. Okay, that's usually why in any sport where you're involving hitting somebody, you want to get low and get small so that that force that's exerted back on you is exerted on all of your mass. That prevents you from being injured. Okay, everyone kind of follow me on that? Okay, same idea behind basically all safety equipment in sports. Okay, especially helmets. All right. The purpose of a helmet is to make sure that a force cannot act on a small localized piece of mass, okay, like a small portion of your skull. If you get hit with a helmet on, then that force is distributed over the entire head. Okay, and so as a result, you're not likely to get a skull fracture. Okay, you may still get a concussion, but you may not get a skull fracture in that one localized area. Everyone kind of follow there? All right, so we were talking about, if I have something sitting on a table, okay, that gravity pulls the book into the table pushes back up on the book. That's an action-reaction pair. If you've ever blown up a balloon and let it go and then giggled as it flew around the room making that fart noise, okay, that's just the exact same thing, okay? The gas inside is pushing on the balloon, okay, and making it go, but the balloon is squeezing the gas at the same time. It's an action-reaction pair. In fact, that's the simplest form of rocket engine there is, okay? Compressed gas in a balloon. Right? Obviously, we have a much more controlled way of doing that with real rockets. Otherwise, we don't want them to do that. It's generally bad. Okay. All right, everyone kind of following me here with the action-reaction stuff? All right, consider this situation. For some reason, I'm in this boat and I've lost the paddle. I need to get out of the boat and onto the dock, but I can't swim. I can actually swim, but not very well. Okay, but in this case, I can't swim. So I'm going to run along the boat, jump off the boat, and onto the dock. What are my chances? Actually, my chances are very good if I do it right. Okay, what everyone pictures is that as I'm running along the boat's going to move backwards on me. Is it going to do that? It is. It's going to do that. Okay, there's nothing I can really do to stop that except that I want to direct my force more which way? Downwards. Okay? If I direct my force downwards, I'm not just pushing on the boat, I'm pushing on all the water underneath. Okay? That's a much greater mass. It's going to experience a much smaller acceleration. If I just push backwards on the boat, yep, I am going to face plant and lose all my teeth right here. Okay? I don't want that. So if I get to the end of the boat and jump by pushing downwards at an angle on the boat and the water have to push back with an equal and opposite reactive force on me. That will launch me into the air gracefully, allowing me to land on the dock and keep all my teeth. Okay? If I push backwards on the boat will push forwards on me. That's fine, okay? But that's much less mass. So the boat's going to accelerate a lot more than I am, and that's not going to work out well for me. Okay? But I could still accomplish this provided I do it right, if I know what I'm doing. Okay, that sort of makes sense to everybody? Okay. All right, so whenever one body exerts a force on the second body exerts an oppositely directed force of equal magnitude back. Okay. All right, so that's our action-reaction law. Okay, so let's do this problem here. It's kind of a simple example of Newton's third law. So I'm in space and I am pushing against my spacecraft. All right, so I exert a force this way on the spacecraft of 36 newtons. All right, I want to calculate my acceleration away from the spacecraft. All right, so what Newton's third law says is that the force on the spacecraft is equal to, but opposite, the force on me, the astronaut. Okay, that's mathematically Newton's third law. Every action is an equal and opposite reaction. The action is the force on the spacecraft. The reaction is the force on the astronaut. It's negative. Ship, spacecraft. Yeah. Okay, so I've got on this side then, how do I calculate this force? Mass times acceleration. Okay, so I'm going to have the mass of the spacecraft times the acceleration of the spacecraft equals the mass of the astronaut times the acceleration of the astronaut, but obviously this is going to be in the other direction. So can I calculate the acceleration of the astronaut? I can't. I know the astronaut's mass, I know the mass of the spacecraft, and I know the force being used. Okay? If I know the force being used, then I can say, all right, I'm just going to break this up. These two forces are the same, okay, and I'm just going to treat them separately. The mass of the ship times the acceleration of the ship equals positive 36 newtons. Okay? The mass of the astronaut times the acceleration of the astronaut equals negative 36 newtons. Okay, everyone follow me there? I just took that formula, this one here, and I said, okay, I know what the force on the ship is. It's 36. The force on the astronaut is negative 36. All right, now, since I know the mass of both, I can calculate the acceleration of both the astronaut and the ship. Okay, which one's going to be bigger? Yeah, the astronaut's acceleration is going to be way bigger because his mass is much smaller compared to that of the ship. Okay, so if we're doing that math here, okay, we'll divide both sides by the mass of the ship, which we were told was 11,000 kilograms. Okay, that'll leave us with the acceleration of the ship, which will be very, very small. Okay, so the acceleration of the ship is like 3.2 or 3.3 millimeters per second squared. All right, much to worry about? You wouldn't think so, and certainly not if it's just going to be one instant of push. It's not going to make a really big difference. Okay, but when we're talking about maneuvering a spacecraft, the thrusters on most of our spacecraft that we have are not very powerful. They just work over long periods of time. Okay, like the New Horizons spacecraft that went to Pluto, okay, there a couple of years ago. On New Year's Day, it actually passed another object in the Kuiper Belt, and they had to do some course corrections for that. The thrusters on there are only capable of creating accelerations of less than 1 meter per second. Okay, 1 meter per second squared, sorry. So they just have to fire them for longer. They're not powerful thrusters. Okay. All right, can I calculate the acceleration of the astronaut? Okay, I just do the same thing, except now I'm going to divide by the mass of the astronaut, 92 kilograms. Okay. All right, so they experience a much greater acceleration.
So if it gave us a direction, then you still need to apply some.
Yes, so that would be negative 0.39 meters per second squared. Because that's all I was given in the question was positive and negative. I could say away from the ship if I wanted as well. That wouldn't be wrong. Okay. All right, how long is that acceleration going to last? Just as long as I'm in contact and able to push on the ship. As soon as my fingers leave the ship, now I'm going to travel at a constant velocity. Whatever velocity I reached during that acceleration is the velocity I'm going to have. It's not a lot, okay, but it's something. I'm not going to accelerate for very long. All right, is that making some sense? Okay, that's about it. That's as easy as they get. And is there any new math here? Like we just used m times a, and you're going to use sum of all forces in some situations too. Okay, Newton's third law just says when one force acts, the other force is opposite. We calculate everything using Newton's second law. All right, so this is what we just did here and what we just talked about. So we'll just skip that. Okay, that's the math we did. All right, so action-reaction situations are responsible for basically being able to do everything, right? When I'm walking, right, I push on the floor and the floor pushes back, okay? It's friction. As long as my foot doesn't slide, okay, then the friction that's there is actually pushing me forward, okay? So last year during their Super Bowl, Nike put out one of the worst ads ever. It wasn't the Colin Kaepernick one. Okay, that was different. This is a physically bad, okay, ad. In fact, I was because I'm crazy. I was like shouting at the TV when it came on because I'm crazy. The ad was this. They had, I think it was Kevin Hart, and he was out for a run, and he got everybody else to run with him, and they spun the earth the other way. Okay, and people believe this crap because they don't think about it. Okay? They're like, oh yeah, if we got everybody to walk at the same time in the same direction, we'd be exerting a force on the earth. It's Newton's third law. We get the earth to spin the other way. No, no, stupid. But people believe it because people are stupid. Okay? So here's why it's stupid. How big is the earth? Yeah. That's the mass of the earth. I get the entire human population together and actually exert a force somehow uniformly at exactly the same time. Okay? I'm talking about a mass that is billions of times smaller than that. Can I exert a force that's going to reverse the earth? No. If that were true, wouldn't jumping knock the earth out of orbit? No, it couldn't happen. The Earth's been hit by really big stuff in its history and it's never been knocked out of orbit. Okay, it's not going to get knocked out of orbit. Okay, or you're not going to reverse the spin of the Earth. Okay, by walking or getting everybody to walk in one direction. We'll do an activity on that later, but it's just dumb. Okay, you can't do that. Okay, but people get this idea when they see that diagram. Yeah, I exert a force on the Earth. So the Earth accelerates. Sure, it does, but the Earth is not this perfectly solid ball that transfers forces that way either. Okay, I mean, yes, there's the crust, and when I push on the crust, yeah, there's deformation, whatever. But there's also that mantle and the core that's rotating and all that kind of stuff. You are not exerting a force that is in any way, shape, or form causing the Earth to slow down. Okay, you're just not. No. Yeah. Like, I mean, if you collect a bunch of mass in a place where it wasn't previously, then you change the distribution of mass on the Earth, which could theoretically cause, something to change in the way the Earth wobbles in its orbit. But we're talking about you got to have a huge amount of mass. Like basically, you got to take half a continent and move it somewhere. Okay, that's the kind of mass you have to move. Now, if we're talking about like a giant volcanic eruption that suddenly deposits a huge amount, like people are always freaking out about this Yellowstone supervolcano. I don't know if you guys have ever heard crazy people talk about that. Okay, I use the term crazy people a lot because there's a lot of crazy people. Okay, where they're saying that this supervolcano, if it erupted, would basically cover North America in a layer of rock, like a kilometer thick. Okay, that'd be bad. People think about these things. See, people have too much time and think about strange things. But anyway, if that were to happen, that would be a massive redistribution of the Earth's mass into a new place. That could affect how it wobbles and orbits or rotates slightly, but not a huge amount. Do you have a question, Angela? Okay. All right. Now we put this to use. There's some ways to put this to good use, Newton's third law. Okay. And one of those ways is if you've ever seen like the people that drive along the Deerfoot with those little U-Haul trailers. Okay. You can rent them, right? The little U-Haul trailers. A lot of those trailers are attached to cars that probably shouldn't tow them. Okay. Like they're way too small. And most of the cars that are small also don't have electrical hookups to operate power brakes. Okay, most trailers, if you've seen them, actually have electric powered brakes that are powered by your car's electrical system. Okay, even if you tow like a big RV, okay, the brakes are electric and they're operated through the tow vehicle. But smaller vehicles don't have this. You just get a hitch attached and then you plug the trailer into the hitch and that's it. You just tow it. It doesn't have brakes that work when you press your brakes. Okay, pressing your brakes doesn't actuate the brakes on the trailer. That's dangerous because of whose law? Newton's first law. Okay, anybody ever seen a trailer jackknife? Yeah, okay. A trailer jackknifes because of Newton's first law. The tow vehicle stops. The towing vehicle keeps going and it'll try to pass the towing vehicle. Okay, and this is what happens on a really icy road with a semi-truck. The semi-truck is able to stop, especially with an empty trailer. It happens a lot more with empty trailers, okay, because there's not a lot of friction on the tires, not a lot of weight on top of them, so they swing around very easily. Okay, so it'll come around because it wants to keep going. Okay, and it just rotates around the hitch. Okay, I actually saw it happen with a guy towing a boat on Highway 22 one time. A gust of wind just picked up the boat and swung it around him. Okay. They do. The problem is that if they lock up, they just slide. Because the tractor part is heavy, it actually starts to stop, but the trailer goes around because there's not enough weight for the tires, that they just lock up and slide, right? So they'll actually try to pass it. So we don't want that, obviously. So what they do is they put on these reaction control brakes onto these trailers. It's a spring-loaded mechanism so that when the towing vehicle slows down, Newton's first law causes the trailer to push on the tow vehicle, and the tow vehicle pushes back on a spring that's right here that actuates the brakes. Okay, so it actually uses the fact that Newton's first law is going to cause the trailer to push on the truck will push back, and that will cause the brakes to actuate. That works under ideal road conditions. If it's icy, the trailer will just go around. Okay, it'll just try to pass because it'll hit that. The brakes will lock for a second, and then the trailer will rotate. The brakes lock, they just slide, they don't slow down, and then you get this Honda Civic towing 5 times its own mass in a small trailer, okay, in the ditch, rolled over with its trailer. Okay, so you got to be careful with that. Okay, cars have a maximum towing capacity for a reason. Okay, and you don't want to tow more than your recommended mass, okay, because it does get very dangerous, especially if it gets windy. Okay, you get that stuff moving and you get sway. Okay, and if the trailer starts to sway, it exerts a reactive force on the truck or tow vehicle or whatever it is, and it'll start to move. It becomes hard to steer and you can lose control. Okay, so all of that stuff is Newton's third law stuff. Okay. All right. So we're going to go over a couple of kind of Newton's third law problems here. Then we'll start out pretty easy and we'll get more complex as we go. Sorry, we already did easy. So here we got 3 boxes. 3 boxes in a row. They're touching each other. They are on a frictionless surface. Okay, and a person is pushing on the first box. Okay, so an applied force causes box A causes all the boxes to accelerate at 1.5 meters per second squared to the right. Okay, we want to calculate the force exerted by box C on box B. All right, this is where it gets like hairy. Okay, these boxes are what we call a system. Okay, so all parts of this system accelerate at 1.5 meters per second squared, the same rate. Okay, so can I separate this system into individual parts? Yes, I can. In fact, I have to. All right. If I'm going to find the force that C exerts back on B, okay, I can't do that using the combined mass of the system because then I'm treating the system as all one piece. Okay. If I'm trying to find a force on an individual part of the system, I have to pull the system apart. Okay. So what I'm going to do here is I'm going to use box C to figure this out. All right. So what's pushing on box C? Box B. Okay, which way is box B pushing on box C? This way. Everyone okay with that? Okay, pushing it to the right. So here's box C, and it is 5 kilograms. All right, this is a frictionless surface. So is that the only force acting on C? Yes, it's the only unbalanced force anyway. Okay, and gravity and normal force are there, but they're not important for what we're doing. Okay, that's the only force acting on box C. So as a result, it's also the net force. Okay, so this is going to be equal to my net force. Can I calculate my net force? Yeah, I know that box C is 5 kilograms, and I know it's accelerating at 1.5 meters per second squared. Okay, so I can go m times a. So 5 times 1.5 equals . Okay, how does that help me? The question wants to know what's the force that C exerts on B. I found out the force that B exerts on C. It's the same, but opposite. Do you see how convoluted this can get? Okay, I found a force acting on box B by finding a force acting on box C, because I knew they were an action-reaction pair. Okay? I knew that the only force acting on the last box was the second box. Okay? And so as a result, the third box would exert a force back on the second box that is the same. No, it'll be a different force between A and B because they're bigger, right? So they'll have a bigger net force, and they'll be, does that make sense? Like if I draw the free body diagram of box B, okay, I'm going to have, the force of A on B and the force of C on B, which I just calculated, right? I know that it's 7.5 newtons. Okay, I could calculate this one because I know now I can calculate the net force on B, right? It's 10 times 1.5, so the net force is 15 newtons, okay? And that's this plus that. So now I could calculate the force that B exerts back on A if I wanted. Yeah. Okay, as long as I understand that those forces are always acting in pairs, okay, I can still use Newton's second law to find those forces and then go, oh, right, well, I found that force, but it's the opposite of that one. It's convoluted, but it's still just Newton's second law. All right, how many people are looking at that and going, oh, crap? Okay, it's okay. This is, again, all that contextual stuff. I'm trying to expose you to as many different situations as possible here so that you see just how convoluted some of this stuff can get. Okay. All right, does anybody need that one anymore? Okay, so for the situation in the previous example, exert the force that, or calculate the force that B exerts on A. Well, we actually did that, okay? We went back here, okay? So we're gonna do that one here now, okay? And I said, all right, here's box B, okay? I wanna find out the force that it exerts on A. Well, the force that B exerts on A is the same as A exerts on B. So I can find this force by finding the net force on B, which was 10 times the acceleration, 10 kilograms times 1.5, okay? And then this force here was the force that C exerted back. All right, so that means then F net equals, okay, 7.5, negative 7.5 because it's backwards, plus the force of A on B. All right, so when I manipulate here, I'm going to get 10 newtons minus negative 7.5 newtons equals force of A on B. So I'll get 17 newtons, 17.5 newtons forward, which means the force that B exerts back is 17.5 newtons to the left. Okay, so I find one, and then I basically just make it negative, so it's acting back the other way. Don't worry if you don't get it right now. We're going to spend some time working on this kind of stuff. I did. No. Well, that would be the net force on A, but not the force that B exerts on A. The force that B exerts on A is the opposite of this. Okay? If I look at A, okay, the forces acting on A are the applied force of the hand, which we were never told, right? And which is negative 17.5 newtons. Okay, so now I can calculate the net force on A because it would be 1.5 times 8, and then I could find out what the applied force from the hand was if I wanted to. I have to work my way all the way backward through all the boxes in order to do that. Okay. But in the end, is this all still sum of all forces in m times A? All the math of Newton's second law. Okay, again, there's nothing mathematically difficult here. It's just a matter of, wow, there's so many forces. They're acting in so many different directions. How do I keep them all straight? Oh, sorry, this was, oh, you're right. Where did the 10 come from? It should be 15. Sorry, I did this all wrong. Yeah, I got going in my head on something. Yeah, it should be 15 newtons minus negative 7.5, so it should be negative 22.5. Yeah, good catch. Okay. So the 15 is the net force on B. I wrote 15 here and then I wrote 10 down here for some reason. I don't know why. Yeah, it's supposed to be 15. I think I confused the mass. That's what I did. Okay. All right. Similar situation. Only 2 boxes though. Okay. Now, so boxes A and B are made of identical materials but have different masses. One's 6.5 kilograms, the other's 8.5 kilograms. They're placed in contact with each other on a horizontal rough surface. So what's present now? Okay. An applied force acting on box A causes both boxes to accelerate at 2.6 meters per second squared to the right. The force of friction on box B is 28.3 newtons. Calculate the force exerted by box B on box A. Use box B to solve this, is the hint that I will give you. Okay, you have enough information to solve this using, the information for box B. Okay, give you a little bit of time. Free body diagram of box B and all the forces acting on it. All right, so if I'm looking at this thing as a system, okay, then the only forces acting on the entire system are the force of friction, which I don't know because they only told me the force of friction on one of the boxes, and the applied force from the hand, which I also don't know. Okay, so I can't solve for a force that's part of this system using the whole system because I don't have any information for that. Okay, all I can calculate about the system right now is the net force, which doesn't help me. Okay, because I don't know either one of the 2 forces that contribute to it. So what I need to do is break this down. I'm looking for the force that B exerts on A. Now, according to Newton's third law, that should be equal to which force? Right, the force that A exerts on B. And there's only 2 forces acting on box B. Okay, box B is 8.5 kilograms, and it's being pushed this way by the box A. Okay, so the force of A on B. That force should be equal but opposite to the one that they want me to find. Everybody all right with that? Yes? Okay, what's the other force acting on box B? Friction. And they told me what that is. They told me it's 28.3 newtons. The last piece of information I have is that the system, and thus the individual parts, are accelerating at 2.6 meters per second squared. So what can I find if I know that the box is 8.5 kilograms and its acceleration is 2.6 meters per second squared? I can find the net force. Okay, so that's what I'm going to do next. F net is m times A, 8.5 times 2.6. All right, so the net force acting on box B is 22.1 newtons. Okay, how does that help me? Right, I know the total, and I know one of the 2 that contribute to it. Can I solve for the one I don't know using sum of all forces? Yes, I can. Okay, so F net is also going to be the force of A on B plus the force of friction. Okay, so I can solve for the force of A on B by going F net minus the force of friction. So that's going to be 22.1 newtons minus negative 28.3 newtons. I have to make friction negative because it's in the opposite direction of the net force. Everyone okay with that? Okay, so I'm going to find that the force of A on B is 50 newtons, which means the force that B exerts back on A is also negative 50 newtons. Okay. All right. So sometimes it helps to draw like I did here. I drew a free body diagram of the whole system, and that told me I can't use the whole system. I didn't have enough information. Then I drew a free body diagram of one of the boxes, and I found that I did have enough information to calculate what I needed with that. Okay, I didn't draw a free body diagram of box A But if I had, it would have told me that I still didn't have enough information to use this diagram, okay? Because I would have had the applied force and the force of B on A and the force of friction. And I didn't know any of those. So there was no way for me to use that box to calculate what I wanted. Everyone follow me on that? Okay, so that's kind of the thought process that I go through as I'm trying to solve one of these problems is, okay, can I use the whole system? No. All right, can I use this part of the system? No. Can I use this part of the system? Yes. Okay, and then I go with that one.
The force applied on this 1.5 kilogram.
The force that B exerts back on A is negative 50 newtons. Okay, so that would be this force. That would be after all that work that I've done. That's still the only force I know on A, right? I still can't calculate this force, like the original hand pushing force, because I don't know what this force is, okay? And there's no way for me to calculate it. I can calculate the net force, but that doesn't help me because I still have two unknown parts of it. Yeah. But it's okay because they didn't ask me for that. I was able to calculate this force by using another part of the system and Newton's third law. All right. Any other questions on that one? Okay. I want you guys to try this question, okay? It's very similar to what we've been doing, so you can kind of use the last two questions to work your way through it, right? So the context here is that they're using these horses to pull these logs through the forest from an area that they're cutting, okay? And a light chain is connecting the two logs, okay? So the picture of this, okay? And then for part B, they tell you that the force of friction on log A individually is 900 newtons, right? So part A, fairly straightforward to solve. Solve it as a system, okay? For part B, you can use either log to solve for what they ask for, okay? Either log will get you the answer because you have enough information for it, right? I'll give you a bit of time on that one. All right, so in part A, they want to know the acceleration of the logs, in other words, the whole system. And right now I can calculate that very quickly because I know that the total backwards force on the entire system is 2,400 newtons, the total forwards force is 2,600 newtons, so my F net on the entire system is 200 newtons in a forward direction, okay? If I want to calculate the acceleration of those logs, I take that 200 newtons and I divide it by the mass of the system, okay, which is 400 kilograms. And that's going to mean my acceleration is 0.5 meters per second squared forwards. Okay. Do I need that to do part B? I definitely need that. Okay. I cannot do part B without knowing the acceleration of the logs, plural, or each individual log, which is still the same number. Okay. So whichever log you choose, because I did tell you you could solve part B using either log, you will need to find the net force on the log you choose. Okay, that will help you to find the force you're trying to find. Okay. If it were me, I would solve this using log A. Okay, you can solve it using log B, but there'll be one extra step. Okay, you can solve it directly using log A. All right, give it a few more minutes. In case you're wondering, that's the answer down there. 1.63 times 10 to the 3 newtons backward, okay, is the tension in the chain connecting them. All right, I'm going to choose to solve this using log A for two reasons. Okay, and this is my thought process as I go through this. When I read part B, it is asking for a force on log A. Okay, it's saying calculate this force that's acting on log A. And it gives me another force that also acts on log A. So it makes sense to go with that. It's asking about something on log A. The second reason I want to do that is I clearly have more information about log A than I have about log B. Okay, so my chances are pretty good to solve this using the first log. All right, so I've got 150 kilograms. Okay, that's log A. I know that there's a force of 2,600 newtons pulling forwards on log A. I know that there's a force of 900 newtons acting backwards. That's friction. What else is pulling on log A? Log B. And that's the force they want me to find. In other words, it's the tension in the chain between the two logs. Okay? It's also going to be the force pulling forwards on log B. Okay? If it weren't for that chain, log B would move. Okay? So I'm finding the force that B exerts on A because that's what they're asking for, and I can use log A to find that. What do I need to figure out about log A right now? I need to find the net force. Okay? I know that the acceleration of the logs is 0.5 meters per second squared, and I know the mass of log A. Everybody with me there? Right? So that's the first thing I'm going to calculate is F net. So M times A, 150 times 0.5 is 75 newtons, and that's going to be forwards. Okay? The net force on log A is forwards. All right. What's the other way to calculate net force? Sum of all forces. All right, so F net equals, okay, 2,600 newtons, positive, okay, plus negative 900 newtons, plus the force of A, or force of B, sorry, on A. So I know what F net is. It's 75 newtons. I know everything except the force they asked me to find. Everybody all right with that? Okay, so what I'm going to do is manipulate for the force they want me to find. So I'm going to have F net, which will be 75, so positive 75, minus 2,600, minus negative 900, force of friction, okay, equals the force of B on A. Okay. So I'm going to have 75 minus 2,600, or plus, or yeah, minus 2,600, so minus positive 2,600, and then minus negative 900. Okay, that's 1.63 times 10 to the 3 newtons, and it gave me the right direction. B is pulling backwards on A. Would you agree? I mean, think about it. If you're walking normally, okay, that's pretty easy. If somebody says, grab this wagon that's full of bricks and do the same thing, is it harder? Yeah, you can feel the wagon pulling backwards on you, okay, because it's a weight, it's a mass behind you, okay, that is slowing you down.
Because it's the chain and it would be tension, would you still need a direction?
Well, but I would in this case, because it didn't ask what was the tension, it asked how hard is B pulling on A. So that would be a directional force. Had it said what's the tension in the chain, then I'd have just said 1.63 times 10 to the 3. Okay, everybody all right with that? So what makes this tough? I mean, if I'd have given this to you as a Newton's second law question, you probably would have soared right through it, because you've done so many Newton's second law problems that were way harder than that involved using trig and using the friction formula and all of that. Okay, you just soared right through it. But because I introduced it as a Newton's third law problem, it seemed somehow different. Okay, in the end, was it any different? No, we did M times A and sum of all forces. Okay, it works exactly the same. All we need to remember about Newton's third law is that if a force acts on an object, the object exerts a force backwards of equal magnitude. That's it. Okay? That allows us to sometimes figure out forces on objects that we don't have a lot of information about. Using objects we do have a lot of information about. Okay, like those boxes or the first log or whatever. Okay? Now, I did tell you that there was a way to solve this using the second log, so I'll show that as well here. Okay. Okay, so this is log B. I'm trying to find this force. That's the tension in the cable. how much B is pulling back on A with. Everyone all right with that? Okay. There's a force of friction backwards on log B. They don't outright tell me what it is, but they told me the total friction on the system is 2,400, and 900 of that was on the first log. So how much is left? 1,500. Right? So I can calculate same thing, okay, just using the back log now that I've done that extra step. It was just a subtraction operation, but it's an extra step. Okay, so I'm going to calculate the net force on that log. So 250 times 0.5, okay, is 125. Okay, so the net force is positive 125, and then the net force is, in this case, the force of A on B plus the force of friction. So the force of A on B is going to be F net minus the force of friction, which will be positive 125 minus negative 1,500, which gives us 1.63 times 10 to the 3 newtons. Okay, gives us the same answer because it's the same force. All right, you may. All right, are we starting to see that a little bit? Okay, the thing that's difficult about this is being able to go, okay, I figured out all the forces on this box. That's great. Now I need to figure out how that applies to this other box that I don't have as much information about. Okay, it really is very visual. Okay, you have to be able to visualize those forces, put them on the free body diagram, and figure out which ones are which. Okay, that's the tricky part. Okay. I think I'm going to have you guys go back now. There's a couple of questions from the worksheets that I'm going to specifically ask you to do here at this point now. All right, so we'll have you try question 11. If you get question 11, then you can try question 12 after that, but let's do those two for now. All right, so with number 11, what I want to do is identify all the individual forces acting on the system, right? So we're told that the ramp is frictionless, which is good. The pulley is frictionless, right? So the forces that are acting then are the force of gravity on the second mass and F parallel on the first mass. Okay, those would then be the only forces because there's no friction involved, okay, in this system. Everyone okay with that? All right, so can I calculate those two forces? I can. Okay, so this one here, this is a 2.5 kilogram mass. Okay, so I'm going to go 2.5 times 9.81. All right, so I've got 24.525 newtons acting that way. And then I've got to calculate F parallel, which means I've got to do this thing that I usually do here, okay, in order to find F parallel. All right, so this side here will be FG. This is a 30-degree angle. So this side here is FG. This is 2 kilograms. So 2 times 9.81 is 19.62 newtons. And then I find F parallel by going sine of 30 times 19.62. And this throws people, so they don't like getting this number. Okay, but F parallel acting on that mass is 9.81 newtons, not meters per second squared, but newtons. It just worked out that way. Okay, so this force here, F parallel, happens to be 9.81 newtons. All right, those are the only two forces, and this is a system. What do I do with a system, especially when it contains a pulley? Well, before I do sum of all forces, I want to do the sum of all forces on the entire system. So I'm going to simplify this diagram. I got 4.5 kilograms being pulled this way by 24.525 newtons, and this way by 9.81 newtons. That's what's going on here. Okay, it looks a lot more complicated than that because I threw an inclined plane and a pulley into the same question, but there were only two forces that were acting here. Gravity on the hanging mass and F parallel on the mass that was on the incline. Okay, so when I do this, I should get, so minus 9.81 will give me 14.715. So my net force is 14.715 newtons. And that's going to be accelerating 4.5 kilograms worth of mass. So 14.715 divided by 4.5. Okay, so we're looking at 3.3 meters per second squared because we only have two significant figures here. Okay, and I can't give a vector on that. Oh, sorry, I can because it asked about mass 1. So I can say up the ramp because it did specifically ask about mass 1. All right. So sometimes it's possible to make a question look really difficult when in actual fact, not a lot to it. Guys, last year, that was a final exam question. It went poorly, quite poorly, okay? Because people just shut down. As soon as they saw it, they're like, inclined plane and a pulley, I quit. Okay, and that's what they did. Instead of going, man, there's only two forces in that question. Okay, all I have to do is find them both and do sum of all forces. In the end, mathematically, again, not difficult. Okay, I think I've said that same thing like 100 times since we started doing Newton's second law. All right. This is why, guys, you don't have to be good at math to do physics. Okay, because the math isn't that hard. It's figuring it all out that's hard.